All right, today we are looking at differentiating between speed, velocity, and acceleration. Actually, today we're only looking at the speed and velocity. We'll hit acceleration maybe tomorrow. You're going to view the lesson, complete the questions, and then you have some questions to do in your notebook that are in Schoology. So our essential question, how can we describe the motion of an object relative to a reference point? Sounds like a lot to say how can we describe the movement of an object. Some vocabulary words you may need to know are scalar, meaning measurements that tell how much, for example, length, speed, or temperature, and vector, which you've had before when we talked about net force, measurements that tell both how much and which direction. So examples, weight, velocity, displacement. So what is motion? Motion is the change in position of an object relative to a reference point. So the reference point in this one is the duck. The shark is moving fast relative to the bird. And then the snail is moving quite slow, but he is moving relative to the grass. So he's, compared to the grass, he's moving fast. So what is motion? Ask Galileo, if the Earth is spinning at 1,000 miles per hour and also moving 67,000 miles per hour in orbit around the sun, why can't we feel the motion? Well, this short little video clip answers that question.
If, like a galloping horse, the Earth is moving through space at great speed, why can't we feel the movement? Galileo thought it was possible that the Earth could spin on its axis fast enough to cause night and day without anyone being able to feel the motion.
What is really exciting about Galileo, and you see it exactly the same in Einstein too, was the way he picked up what seemed to be an absolute impossibility. He said, we have this incredibly strong evidence that the Earth is not moving. Everything that our senses tell us is that the Earth is not moving. And yet, Copernicus has got these rather strong arguments from astronomy to suggest that the Earth is moving. So then Galileo says, well, this actually should tell us something very deep about how nature works.
In Galileo's thought experiment, a horse represented the motion of the Earth. If the rider dropped the ball while the horse was standing still, the ball would, just as one might predict, fall straight down, landing beside the horse. But, Galileo thought, what would happen if the ball was dropped while the horse was moving through space in a gallop? Would the ball now fall behind the moving horse? No, thought Galileo, for in his thought experiment, the forward motion of the horse would be translated through the rider's hand to the ball, so that when the ball was dropped, it too would continue to move forward, landing beside the horse just as before. He thought when the horse and the ball shared the same forward motion, it appeared as if the motion didn't exist. So, Galileo reasoned, it is possible that, like the ball and the horse, we are sharing the motion of the Earth without being able to feel it.
There is a sort of a principle of relativity where if you're sort of moving with the Earth, everything shares the same motion. Not only is the Earth moving, but I'm sharing that motion as well. And therefore, it is all hidden. It was probably the first really great thought experiment in physics. In fact, he was so confident of the result, he never bothered to do the experiment to show it was right.
So what is position? A coordinate system is helpful for describing the position of an object relative to the reference point, also called the origin. In this diagram, the gas pump is the origin, so we can label its position 0. The position x of the front of the pickup truck is x equals positive 6 units, and the position of the front of the car is x equals negative 2 units from the reference point. What is displacement? Well, displacement is the change in position. So it is a vector, meaning that it has a direction as well as a magnitude or amount. So displacement equals the final position minus the initial position. You don't have to worry about calculating that. So therefore, the car's displacement is 9 minus 4, which equals 5 units in the positive direction. So remember, displacement includes a direction, and without a direction, it is simply the distance traveled. So we do all of that to get to what is speed. So speed is the rate at which an object moves a distance in a given amount of time. So there are two types of speed. There's average speed and instantaneous speed. And in 8th grade, we generally deal with average speed. So average speed is the total distance covered in a given amount of time. A runner's average speed during the marathon would be found by dividing the total distance by the total time it took to run the marathon. So speed equals distance divided by time. Instantaneous speed is the speed of an object in a given instant. So the plane's instantaneous speed is given by the speedometer, which measures the distance the plane is traveling per unit of time. So we don't really worry about that, but it's just like if you were in the car with mom and you look, she's going 55 miles per hour. Well, that's in that moment. That's not her average speed for the entire trip. So either way, the units are always a distance unit over a time unit, like miles per hour or meters per second or kilometers per hour. So it's always a unit of distance over a unit of time. So what is velocity then? Well, velocity is the displacement of an object over a given amount of time. Remember, displacement must have a direction. So it's speed of an object with a direction. Velocity is a vector. So the turtle's velocity is 4 meters per hour east. His speed is 4 meters per hour. So you have to have the direction for it to be a velocity. How do we calculate an object's velocity? An ambulance travels north to an accident 10 miles away. It takes 4 minutes. So what is the ambulance's average velocity? Well, the speed triangle is helpful for finding the distance traveled or the time passed. So to do the speed triangle, you draw a triangle and you put a T inside. And then you write the formula for speed going from left to right. So speed is distance over time. So D is going to be at the top. So distance at the top and then speed and time at the bottom. So this helps you keep it straight when you had to solve for something other than speed. So if you need to find the distance traveled, you multiply the speed by the time. If you need to find the time that something was traveling, you divide the distance by the speed. And the trick is just to cover up what you want to find the formula that you need. So you just take your finger and cover up one of the letters and it gives you the other formula.
Which travels faster, Usain Bolt or a Formula One car? In this video, we'll find out how to calculate speed using distance and time, which we'll then use to work out the answer to who's faster. Speed is a measure of the distance an object travels in a certain time. Speed can be calculated using the formula speed equals distance travelled divided by time. So, to work out which is faster, Usain Bolt or the F1 car, we need to know how far they both travelled and how long it takes them to cover that distance. Let's work out the speed of Usain Bolt first. In 2009, Usain Bolt set the world record for the 100-metre sprint in 9.58 seconds. The distance was 100 metres. The time taken was 9.58 seconds. Using the formula of speed equals distance divided by time, 100 metres divided by 9.58 seconds means his speed was 10.44 metres per second. We have the units for distance and time, metres and seconds, which we use to work out the units for the speed. Metres divided by seconds, which we say as metres per second. That's pretty impressive. even for the fastest man on Earth. So how fast is an F1 car for us to compare him to? Pause the video and work it out. Did you get 375 kilometers per hour? So who's faster? From these speeds, we can't tell. What's the problem with comparing these two answers? Pause the video and have a think. To work out which is travelling faster, the units of speed must be the same. So let's convert the Formula 1 speed also into meters per second. Kilometers into meters multiplied by 1,000. And turn 1 hour into seconds by multiplying by 60 for minutes and then 60 again for seconds. So 375,000 meters divided by 3,600 seconds gives us 104.2 meters per second. Now we have our speeds in the same units, it's easy to see that the Formula 1 car is much, much faster. The formula can also be written in a formula triangle. Speed equals distance divided by time. Time equals distance divided by speed. And distance equals speed multiplied by time. Here are 2 questions for you to do. Pause the video and work them out. Did you get them right? A distance of 150 kilometers and a time of 1.66 hours, which is 1 hour 40 minutes. So now you can calculate speed, distance and time and understand a little bit about the units of speed, and of course have proved that a Formula 1 car is faster than even the fastest person on the planet.
So in your notebook now, you're going to go to page 58, which should be the next page, unless I messed up. It's very possible. But you're going to go into Schoology, and there are 13 practice problems that you are going to solve in your notebook. You may use a calculator. I have no problem with calculator. That is not an issue. You also get a calculator when you take the Science STAR test. However, you do need to show each step. So you'll write the equation you used, plug in the numbers, and then you will write your answer with the correct units in order to get credit during the notebook check, okay? And that will be it for today. Thank you guys. See you tomorrow.